Pleasant day to everyone. Today we will be discussing about the vertical stress caused by a vertical strip load which has a finite width and an infinite length. So this is your unit 4, the unit 4 of our module T, which still talks about the stresses in a mass soil. First, we take a look at the figure. This is your vertical strip load. It says that it has a finite width because the width is defined or it is exact. And then it is infinite length because we do not know the value where the length will cut or will end. We have here your point A, and we want to know the effect of this certain vertical strip load at this point in the given soil. So point A has a depth of Z and has a horizontal distance of X from the midpoint of the vertical strip load. So to know the vertical stress increase at point A, we will be using this equation. So as we can see, it is a very lengthy equation, but actually there are only few parameters. It was just used repetitively. So the parameters are first is the Q, which is the load per unit area. And then we have Z. So Z is the depth from the soil surface up to our point of consideration. And then we have the X parameter, which is the horizontal distance measured from the midpoint of the strip load up to the point of consideration. And then finally, the B, which is the finite width of the strip load. So as you can see, it is a lengthy equation, but there were only few parameters to be used in the equation. Before we go further, there are a few reminders that we have to put into mind in solving problems concerning the vertical strip load. From the equation, the terms in arctangent must be converted to radians. So this term and this term must be converted to radians. Next, if the horizontal distance, which is x, is greater than or equal to b all over 2, or the width, half of the width, we will be using the same equation. However, if the horizontal distance is less than b all over 2, we will be coming up with a negative value. So if x is less than b all over 2, we replace this term with this term. So you can observe that the term is exactly the same except that we added the value of pi. So by adding the value of pi, we will not be coming up with a negative value. The next method that we can use to solve for the vertical stress increase is by using table 3.4. So the table 3.4 is entitled variation, the variation of vertical stress over Q with respect to the value of 2x all over B and 2z all over B. So the first step that we have to do is to determine the value of the 2z all over B and the 2x all over B. So from the table, we will be able to identify the value of C, and after determining the value of C, we can substitute it to this equation so that we'll be able to solve the vertical stress increase at a given or at a certain point. So let's take a look at this example. Refer to figure 3.13. A strip load of Q is equal to 43 kilonewton per meter squared is applied over a width B, which is 10 meters. Determine the increase in the vertical stress at point A, located at Z is equal to 4 meters below the surface, given that X is equal to 8 meters. So we have here your figure. It has a width of 10 meters. The load is given to be 43 kilopascal. And then we will determine the vertical stress increase at point A as an effect of this vertical strip load. So point A is 4 meters deep and 8 meters from the center of the strip load. So first is that we will use method 1, or we will use the equation that is given. So first is we will use method 1, or simply using equation 3.23. In using the following equation, first things first, we have to check the value of x if it is greater than or if it is less than b all over 2. Again, we recall that When x is greater than b all over 2, we will be using the original equation given. When x is less than b all over 2, we will be using the modified equation. The difference of the two equations is simply the addition of pi on the second or on the modified equation. That is because when x is less than b all over 2, we will be coming up with a negative value. Thus, the addition of the pi to the original equation. So going back to the problem, our x is 8 meters and our b is 10. So 10 divided by 2 is 5 meters. 8 meters is greater than 5 meters. Therefore, we will be using this equation. Going back to the figure, we will enlist all the given so that it would be easier for us to solve. Q is equal to 43 kPa, Z is 4 meters, X is 8 meters, and B is equal to 10 meters. We can now take off the figure. We observe that all the parameters from the equation is given. We know the value of Q, it is 43. We know the value of Z, which is 4 meters, the value of X, which is 8 meters, the value of B, which is 10 meters. And then all the parameters are repetitively used in the equation. So therefore, we can simply directly substitute the equation with the given parameters. However, we have to take note that the quantity in arctangent must be converted to radians form. Simplifying, vertical stress increase at point A, that is 43 kPa divided by pi, multiplied by the quantity 0.97 minus 0.98 minus 0.199. So 0.927 and 0.298 has already been converted into their radians form. So therefore, the vertical stress increase at point A is given to be 5.844 kilopascal, and this is now our answer. So using the same problem, we will try to get the vertical stress at point A using table 3.4. The first step in method 2 is to determine the value of 2z all over b and 2x all over b. We recall that z, or the depth, is 4 meters, x is equal to 8 meters, and b is equal to 10 meters. From there, we substitute 2z all over b, that is 2 times 4 divided by 10 is 0.8. And then the value of 2x all over b, that is 2, our x is 8 meters, the width is 10 meters, so this is 1.6. We now refer to table 3.4 for us to identify the value of c. So from the table, the value of 2z all over b is 0.8, so that is somewhere here. And then the value of 2x all over b is 1.6. And where the two intersects together, this now becomes the value of our C, 0.137. So from the table, C is equal to 0.137. We now substitute the value taken from the table to this equation. Vertical stress increase divided by Q is equal to C. We cross multiply. That becomes 43 kPa times 0.137. Vertical stress at point A with the use of the table is 5.891 kilopascal, and this is now our answer. So if we compare it with the value we had a while back when using method 1, it is almost equal. So that is now identifying the vertical stress caused by a strip load.